Good. And now we move to the last talk, although this is going to be a talk on two merged papers. So actually we're going to have two talks of half the time each. Okay. So we are starting with the Xinrui. If you can, yeah, you are unmuted, that's good. Okay, now you're sharing the screen, that's great. Good. Okay, so I guess she will start with the first topic about fair, colorful K-center clustering. And then we are going to a technique for obtaining two approximations for K-center with covering constraint. Okay, thank you very much. The floor is yours.
Okay. Thanks for the introduction, and thanks everyone for joining. Yeah, so I'll be talking first about this colorful K-center problem. It's joint work with Georg and Ulla Svensson. And then second half, Georg will be presenting the work of his and his colleagues at ETH. So to get right into things, let's start first with the original K-center problem. So you're given a set of points P and an integer K, and the goal is to find a set of K-centers so that you minimize the maximum distance of any point to its nearest center. In other words, if we draw circles around these centers, then we want to minimize the radius required to cover all of the points. Then we can generalize this problem slightly to the version with outliers. Now you have another parameter m that tells you that only m of the points need to be covered. So in this case, we've left 4 of the points uncovered, and we have slightly different solution set with a different radius. Now we can go on to the colorful K-center problem, which is the main point of this talk. The points are given to you now colored red or blue. And like the outliers version, each color has its own coverage constraint that tells you how many you should cover. So in this case, we've covered 5 red, 5 blue with 3 centers. So clearly we can state this problem for more colors, but to keep things simple here, let's just stick with red and blue. And by the end, you'll see that it can be easily generalized. And it's known that to do better than 2 approximation, that is to get the radius no more than twice the optimal, is NP hard. So why study this problem? Well, first, there's some sort of fairness constraint. In the outliers version, it could be that the points represent different types of elements, and maybe all the elements of one type are outliers in your solution. While now with colors, we can encode the different types and give every type some sort of service guarantee. Then from an algorithmic point of view, this generalizes the K-center with outliers problem, but also there is a new algorithmic consideration that we didn't have before, which is that now we have a K subset sum problem within a colorful K-center. So let's ignore the numbers here, but to put it simply, given your K subset sum problem, we can put certain numbers of red and blue points in small clusters, and then spread these clusters far apart so that your K subset sum is a yes instance if and only if you can open up a small radius around K of these clusters to satisfy the coverage constraints. Otherwise, you have to open up a much larger radius that will cover at least 2 of these clusters at once. So the separation tells you if K subset sum is yes or no instance. So I'll talk a bit more about this in a bit, but first let's summarize what has been done already. So this problem was introduced in a recent ESA paper, and what was done was a pseudo approximation that opens K+1 centers, but using radius no more than twice the optimal. And then for a true constant factor, they did the case of just 2 colors in the plane. And now we have a 3 approximation for any number of colors in any metric space, and also some integrality gap results for some LP strengthening techniques. Then later, you'll hear about a different approximation that uses quite different techniques and some hardness results. So I'll actually talk about the second bullet point first. We were able to show that if you apply the sum of squares hierarchy to the standard LP relaxation with a linear number of rounds, then you still have an unbounded integrality gap. And we did a reduction from this result of Grigoriev that says if you sum up these 0, 1, 2 copies of these 0, 1 variables to an odd number, then clearly there's no integer solution, but sum of squares will not recognize this with the linear number of rounds. But then this looks like a subset sum problem. So like before, we can place certain number of points within small clusters and then spread these far apart so that sum of squares thinks you can open up a small radius and assign fractional variables to these clusters. Well, actually, you can get the integer solution to be arbitrarily large because it has to cover at least 2 of these clusters at once. So on the other hand, if we know that we have to solve this subset sum problem, then we can add flow-based inequalities that model the dynamic program. But then the problem here is when your clusters are overlapping and then points are overcounted. So it's interesting because on one hand, if you already have the clusters, you still need to solve the subset sum problem. But on the other hand, you can't solve the subset sum problem and ignore the clustering aspect. So to hope to get anywhere, we really have to solve both of these issues at once, which is what we do in the details of our algorithm. But first, to get the main idea, I'll have to talk a bit about the pseudo approximation. So what they do is they take the standard LP relaxation and use a feasible point to get some sort of greedy clustering. Then they feed these clusters into a second simplified LP that just picks out which of these clusters should be opened as centers. And it turns out that at least for 2 colors, an extreme point to the second LP will have at most 2 strictly fractional variables. So if K is 4, then there are 3 variables set to 1 and maybe 2 more that sum to 1. So the easy thing to do is just round both of them up, and then you'll get your K+1 centers. And from now on, we can assume that the optimal radius is normalized to 1, since with these 2 LPs, we can try all the n² pairs of interdistances between the points. But then this leads to a really natural idea, which is when we look at the 2 fractional centers, one of them will have more blue points. So if we just round that one up to 1, then we have already satisfied the requirement for the color blue. And if we want to close the other one to only get K centers, then we lose some red points, but then maybe we can expand the other balls to gain enough red points to make up for that. So using this idea, we kind of have 2 sub-instances. One of them is what we call not well separated, which means that we have 2 balls in an op solution that are close enough together that we can take some point and expand the radius by a bit to cover both of them at once, because then that takes care of the K+1 when you run the pseudo approximation on the remaining points. And this is actually where we get our 3 approximation, because first we try all the points and see if we can use a ball of radius 3 to cover at least 2 balls of opt. And this is the easy case. So when we don't have this property, then the opt solution is kind of well separated in some sense. And we know that intuitively, we're going to have to solve a subset sum problem somewhere. So to get into more details about that, our first phase is the phase where we try to get more red points. So it turns out that we should guess a couple of points in opt solution so that if P is the ball of opt, then we want Q to maximize number of red points in this flower structure here, which is all the shaded regions. Then the point is that instead of opening a ball around P, we can open a ball of radius 2 around Q to cover this original ball that should have been in the opt solution, and also all these extra red points. And we use separatedness to ensure that all the red points are indeed extra and not part of another ball of opt. So what we like to do now is just set some of these aside and then run the pseudo approximation on the remaining points. But we can't quite do that because the clustering in the pseudo approximation might still form these clusters that are too dense, that have too many red points in relation to the number that we've gained. So we would just like to remove these dense points. So it turns out that they look something like the diagram on the right. Keep removing these sets until we can be guaranteed that running the pseudo approximation on the remaining sparse points doesn't give any clusters that have too many red points. And we can't just throw these dense sets away because they might contain some balls of opt. And the only thing we need here is that a ball of opt, it should either be completely inside a dense set or completely disjoint from it. Because then we don't kind of destroy the opt solution that we need for the pseudo approximation to work. So this is just some property that we have to prove. And the proof essentially boils down to these two pictures, which I won't get into the details of. And then the point is that we can use dynamic programming to extract exactly the balls of radius 1 that we should add to our solution from these dense sets. So if we guess the number of red and blue points and the number of centers, we verify with the dynamic program. And in the correct iteration, we'll just run the pseudo approximation now on the remaining sparse points. So we've guaranteed that no fractional center will have too many red points. So we can just close the one with fewer blue points. And we've only used at most balls of radius 2. So we have a true approximation for these well-separated instances. And it's quite easy to generalize this to gamma number of colors, because instead of 2 fractional centers at the end, we'll end up with roughly gamma many. So at the beginning, we should guess about gamma many centers for each of the gamma colors. So this is why we have a gamma squared term in our exponent of the running time. And recall that overall it's a 3 approximation when we consider the easy case of not well-separated instances. So clearly an open question here is to do a true approximation for all instances. And we think that this would require new techniques because this follows the pattern of previous case center problems where it was easy to do a 3 approximation, but much harder to get down to 2. And one possible direction is to combine the Lasserre hierarchy with the flow-based inequalities, because if you recall, one of them took care of the clustering aspect and the other one took care of the subset sum. So it's reasonable to suppose if you combine them together, maybe you will get something. So that's all I wanted to say. So I guess in the interest of time, we'll take questions at the very end, and I'll pass things off to Georg.
Thank you, Xinrui.
Yeah,
can you all hear me? Can you all hear me?
Yes.
Wonderful. And you can see the same slides? Wonderful.
Yes.
Great. Let me take this opportunity to thank the organizers for moving this conference to the digital space and making it available to everyone free of charge. Now let's get into it. I'm presenting another paper on a similar problem. This was work done with Haris Anahidakis, Adam Korbish, Rico Zenklusen, and we're all at ETH. I'm going to introduce a slightly more general problem, which is the so-called lottery model for a colorful case center. This applies to any kind of clustering with outliers. What's the problem with outlier clustering? Well, suppose this is our instance of a colorful case center clustering, and let's suppose this is a feasible solution, so that covers enough red and blue points. Now we have some extra points here that are not considered by the clustering because the only constraint is to cover enough points of each color. Now what happens if those points have some desire to be covered or to be contained in some clustering? What we could do is we could consider another clustering where we just copy, let's say, these two clusters from the clustering on the left, and then just add a third one like so. And now we just flip a coin between these two clustering, decide which one we take, and then we have a guarantee that each kind of group of outliers here is covered at least with some probability. And this is exactly what the goal in this lottery model is for outlier problems. You can think of this as the colors providing some sort of group-wise constraints or fairness for subgroups or demographics. And these probabilities for the clients add on top of that kind of individual guarantees. Why is it called a lottery model? You can think of these probabilities as kind of the price that you're paying to enter a lottery. And the higher your probability, the more likely it is that you're covered by the clustering that we draw. This problem was introduced by Harris, Spencer, Srinivasan, and Trin in 2017. And they gave a 2 pseudo approximation for this problem, where the 2 is relative to the radius. All approximations are relative to the radius. And that violates both the covering requirement, so number of points that you want to cover, and also the success probabilities by a 1 minus epsilon factor. So similar to the colorful case center, there's only a pseudo approximation that was known. Now, our contribution is a technique that gives true approximations for case center variants with covering constraints, which includes both of these problems. In particular, we get a 4 approximation for the colorful case center, which I've abbreviated as gamma CKC, where the gamma is just the number of covering constraints, and also a 4 approximation for a colorful case center under this lottery model that I've just talked about. The main components of this algorithmic results are iterative LP strengthening. We've seen the kind of LP results by Xinrui, yet we managed to strengthen the canonical LP using the ellipsoid. This is usually called the round or cut method, which was introduced by Carr et al. And has been used in different contexts. We also rely on this pseudo approximation by Bandeyapada, Inamdar Pai, and Varadarajan that Xinrui's algorithm is also kind of uses. And we use dynamic programming to kind of solve some easy instances. Now, notice that this because of the runtime, this algorithm is only polynomial time for constant gamma, but we also give a hardness result. In particular, assuming P is not equal to NP, this problem is inapproximable if we allow gamma to be unbounded, in the sense that there is no polynomial time algorithm that gives a finite approximation guarantee. And we get the same result if gamma is omega of log P, assuming the exponential hypothesis. So note that this algorithm here, if gamma is roughly log P, it's quasi-polynomial and gives the 4 approximation, and if gamma is omega of log P, then it's inapproximable. Okay, now to illustrate the algorithm, I'm gonna go back to the simpler model, which is exactly the same problem that Xinrui has talked about. So without the lottery, just the colorful case center clustering for simplicity. Now at a high level, what we do, we run the pseudo approximation that opens too many centers, and we'll deal with the violation, and we'll deal with it in a different way than Xinrui's approach. So what do? We start with a fractional clustering, any point that's in the canonical LP relaxation. And we check, we adapt it slightly, but we can ignore that. And we check if it succeeds, because in certain cases it actually does not violate and gives us a feasible solution. And in that case, we're happy and we move on. If it does not give a feasible solution, then we want to use that to kind of gain some information about the fractional clustering we started with. And now the crucial step is that we can relate this information to the existence of certain integral optimal solutions. And it turns out that such separated integral solutions we can actually recover with the DP. And if neither of those succeeds, then we have a guarantee that we can separate the point we started with from PI, the combinatorial polytope. And we can feed that into the ellipsoid, which gives us a new fractional clustering, and we continue. And by the ellipsoid machinery, we are guaranteed that we can only go through this polynomial number of rounds. This is kind of the high level of how the round or cut works. Now note that in the approach that Xinrui has presented, they actually improve the rounding of the pseudo approximation, whereas we kind of improve the instance until the rounding succeeds. So that's kind of one key difference between the two approaches of how we use the pseudo approximation. Now, let me pause here for a second before we dig into the details just a little bit. Okay, so I'm going to give this, one more layer of this round or cut procedure. What is actually happening? So we're starting with a fractional clustering. Any point that is in the canonical LP, so which I've reproduced here. The only thing you really need to know is that the X represents the centers that we're opening, and the Z is to what extent the points are covered. And this constraint here, for example, indicates that we can open at most K centers. Now, what are we doing? The first step is this greedy partitioning that Xinrui mentioned. This is part of the pseudo approximation and part of other clustering algorithms as well. What do? We pick a point, or the highest point in terms of Z. We kind of mark the radius 1 ball around it. I want to call that green, and then we remove radius 4 ball. And then just continue. Pick the next one, mark the radius 1 ball around it, and remove the points that are close until we have partitioned the entire instance, like so. And now, again, the question is, when does the pseudo approximation succeed? This is exactly the condition. So X, again, represents the centers. So if the centers in the green area is at most K minus something, where the something is exactly the violation of the pseudo approximation. So if we're away from K, then we can afford the rounding and we're happy. Basically, we're just assigning all of these points to the central point in each of these clusters and then rounding up. Now, we'd like to know if there are any integral solutions which have this property. Because if not, then that's exactly guaranteeing that this inequality here is true for the point we started with, because we're in the no case here. And if it's not true for an integral solution, then we have a separation from the combinatorial polytope, because it's true for every vertex. So the only thing that's left to check is, can we handle this case? And the answer is yes. Suppose, what does this condition say for integral solutions? Well, this is just saying it has lots of centers in the green area, or most of its centers in the green area. So what we can do is, let's suppose this is my integral solution that has lots of centers in the green area. Now we see that because the green areas are separated by, well, some constant, 3 or 4, radius 1 solutions with centers in the green areas are not overlapping, they're not interacting. And that allows us to recover such solutions with the dynamic program, which also gives us a rounded solution in this case.
Give me 3 minutes.
So to conclude, both of our papers give the first true approximations for the colorful K-center problem. In particular, the EPFL paper gives a 3 approximation, and we get a 4 approximation with a slightly better dependence on gamma. And we can also extend our result to this lottery model, which comes with additional probabilistic constraints. And we also have result that the problem is inapproximable if the number of colors is too big. Where do we go from here? let me just repeat the open questions that Xinrui has mentioned for reference. Again, a true approximation is known for gamma 1, but for any gamma at least 2, the best we have is this 3 approximation. And the question is, can we close this gap? And also, k-median is significantly harder to approximate than k-center, but there's been recent improvement in the k-median with outliers, which is the one color setting, which is also LP-based. And the question here is, can we get constant factor approximations for several color k-median? Thank you.
Thank you very much. And actually, thank to both of you for a very nice presentation. Both of you also, it was good to highlight the difference between the paper. I think you did very well. Do you have any questions from the audience? You can raise your hand or write it in the chat. Okay, I can take one. If you, Georg, if you can go back to the flow chart of like when you gave the scheme, sure, the overall scheme of your.
So you want the slightly
one
abstract
you had 4
one?
approximation and then 2 approximation, and then if not, you would. Yeah,
this one?
Yeah, this one. So did you understand correctly that then your overall approximation of 4 comes because of this first
yes.
questions, right?
Yes,
so,
exactly.
And this is the one that the other paper improves to 3. So I was wondering, can you replace that step so to get the 3 approximation, but with your better running time?
Let me think about that for a second. I don't think so, because we're using the pseudo approximation in a slightly different way, in that we need this clustering to happen with related radius 4 separation, whereas they're using it with radius 2 separation. So that's one difference. So I don't think we can slot it in immediately.
I see. Still work to do. Good. Okay. Any other question? No? Okay. If not, then we can all give a round of applause to all the 4 speakers of today's sessions. Please unmute yourself.